Space is vast, beautiful, silent, and deeply mysterious. Stretching beyond the limits of imagination, the universe is a tapestry of stars, galaxies, and dark voids, each holding secrets we have only begun to uncover. When we gaze into the night sky, we aren't just looking at twinkling lights. We're peering back in time, into a cosmic story that began over 13 billion years ago. A story still unfolding, page by page, in wavelengths we're just learning to read. On a quiet winter sky on December 27th, 1571, in the town of Weil der Stadt in the Holy Roman Empire, a boy was born from a fragile, often ill mind that would one day trace the paths of planets across the heavens. To him, the cosmos was not just a mechanism of motion, but a divine harmony, geometry woven by the hand of God. He gave us the 3 laws of planetary motion, revealing that the orbits of planets were not perfect circles, but elegant ellipses, order hidden within apparent chaos. In his search for cosmic truth, he bridged science and spirit, gazing at the stars not only as a mathematician. He is none other than Johannes Kepler. Kepler's foundational discoveries have made a logical path for us to understand the universe better. But despite the advances of modern science, our powerful telescopes, our deep space probes, our ever-evolving equations, the universe continues to surprise us. Every answer we find seems to raise a dozen new questions. For every phenomenon we think we understand, another appears that shatters our assumptions. It's as if the cosmos is teasing us, revealing just enough to keep us looking, but never quite enough to let us fully understand. From the gentle hum of background radiation echoing from the Big Bang, to sudden bursts of energy from unknown sources, space offers us a puzzle of immense complexity. Some of these phenomena follow predictable patterns. Others defy all logic and scientific reasoning. They hint at forces, dimensions, or civilizations beyond our current grasp. And they remind us that, in the grand scale of things, we may still be in our infancy as a species of cosmic explorers. That's what makes space so compelling. It's not just the beauty or the scale, it's the mystery, the unknown, the feeling that something bigger is out there, waiting. Whether it's buried in gravitational waves, hidden within the gaps of the cosmic microwave background, or pulsing silently from distant stars. The universe is full of questions without answers. In this journey, we'll dive into 5 of the most captivating and confounding mysteries of the cosmos. These are not merely quirks of data or gaps in our knowledge. They challenge the very framework of how we believe the universe works. They force us to reconsider the known laws of physics, the nature of time, and even the possibility of intelligent life beyond Earth. So, as we begin, leave behind what you think you know. Open your mind to the unexplained, and prepare to explore a reality far stranger than fiction. Let's dive into the cosmic unknown. You're watching Space 9, unveiling the mysteries of the cosmos, your gateway to the universe. The WOW Signal 1. Ping from the stars. In the late summer of 1977, amid a quiet night of routine data analysis at Ohio State University, something strange and extraordinary blinked into existence, then vanished without a trace. Astronomer Jerry Amon, reviewing reams of radio telescope printouts from the Big Ear Radio Observatory, noticed a set of alphanumeric characters that defied expectation. A sudden spike in intensity. A signal so clean, so sharply defined, that it stood out like a flare in the abyss of deep space. The moment was so striking, so out of the ordinary, that Eamon circled the data on the printout and scribbled a single, now legendary word in the margin. Wow. The signal had lasted for 72 seconds, the exact length of time the Big Ear could observe a single spot in the sky due to Earth's rotation. It was narrowband, tightly focused around 1,420 megahertz, a frequency known as the hydrogen line, which is naturally emitted by hydrogen, the most abundant element in the universe. This frequency had long been considered a likely calling card for intelligent communication. After all, if any advanced civilization wanted to announce its presence in a universal language, hydrogen, the building block of stars and galaxies, would be a logical choice. What made the signal more compelling was its location. It appeared to come from the general direction of the constellation Sagittarius, near the center of our galaxy. And yet, it didn't match any known terrestrial sources, satellites, military transmissions, or astronomical phenomena. It seemed to emerge from nowhere, peak sharply, and then fade. Exactly what you might expect if a distant, rotating beacon briefly swept across our part of the sky. The scientific community took notice. The signal was real. It wasn't a data processing error. It wasn't radio noise. But despite decades of re-observations, by the Big Ear and countless more powerful radio telescopes around the globe, it was never heard again. So, what was it? Theories poured in. Some suggested it might have been a rare natural event, like a previously unknown type of stellar flare or interstellar plasma interaction. Others considered a signal reflection off space debris or the moon, briefly mimicking an extraterrestrial origin. Some even speculated it was caused by a secret government transmission or a classified satellite we weren't told about. But every hypothesis fell short. The frequency was too precise, the signal too intense. The one-time nature of the detection made it all the more enigmatic. And, unlike most artificial signals we encounter, there was no modulation, no embedded message, no clear pattern. Just a pure, steady tone, like a ping in the dark. And so, inevitably, one possibility lingered louder than the rest. Was it a deliberate signal from another intelligent civilization? SETI, the search for extraterrestrial intelligence, had long theorized that if intelligent life wanted to make contact across the stars, they might send a beacon. A simple, unmistakable transmission in a frequency we would recognize. The hydrogen line, being universally significant and relatively quiet in radio terms, was an ideal candidate. Was the WOW signal such a beacon? A cosmic hello sent by minds unimaginably far away? If so, the message was heartbreakingly brief. No follow-up transmission, no repeated pings, just one burst of potential across the void. And then, silence. It was as if the universe leaned in for a second, whispered something profound, and then disappeared into the shadows. In the decades since, scientists and amateur astronomers alike have searched the same patch of sky, hoping for even a flicker of the original event. In 2016, a new hypothesis suggested the signal may have been caused by a comet passing through the area, emitting hydrogen gas that coincidentally matched the signal's frequency. But subsequent tests and comet observations failed to replicate the strength and clarity of the WOW burst. That theory, like the others, remains unproven. To this day, the WOW signal remains one of the most tantalizing what-ifs in the history of astronomy. It embodies both the promise and the frustration of our search for cosmic company. how a single piece of data can ignite decades of speculation, hope, and mystery. It's a symbol of the unknown, of the vast distance between us and whatever else might be out there. Was it truly artificial? Was it just an anomaly we'll eventually understand? Or was it something else entirely? Something outside our current scientific framework? We don't know. And perhaps that's what makes it so powerful. The wow signal continues to inspire new generations of astronomers, dreamers, and skeptics alike. It serves as a reminder that the universe is still speaking, and we're still learning how to listen. If it was a message, it may have simply said, "We are here." And in the grand silence that followed, it's left us asking, is anyone else out there? Tabby's Star, the dimming enigma. In the grand tapestry of stars that paint our night sky, most shine with steady light, predictable, constant, timeless. But in 2015, a star broke that rhythm and startled the scientific community with its bizarre behavior. Astronomer Tabitha Boyajian, while analyzing data from NASA's Kepler Space Telescope, stumbled upon something deeply unusual. In the constellation Cygnus, roughly 1,470 light-years away, a star designated KIC 8462852 was behaving in a way that defied everything astronomers thought they knew about stellar physics. It wasn't pulsing, flaring, or exploding. It was dimming. Not just once or twice, but repeatedly. And not in any regular, understandable pattern. Soon to be famously known as Tabby's Star, the object dimmed by as much as 22%, and at irregular intervals. For context, a planet the size of Jupiter, our solar system's largest, would only block about 1% of a star's light during a transit. Whatever was passing in front of this star, if indeed anything was, had to be enormous and chaotic. Initially, astronomers searched for a natural explanation. They hypothesized a swarm of comets, perhaps dislodged by a passing star, or maybe clouds of interstellar dust drifting between us and the star. Other theories suggested collisions of planetary bodies, which could have produced vast clouds of debris that temporarily blocked the star's light. But none of these fit the data perfectly. Comets wouldn't persistently block that much light. Dust clouds should have caused infrared emissions, which weren't observed. The patterns were too erratic, too deep, too strange. Then came a whisper from the edge of science fiction. An alien megastructure. Could this be evidence of a Dyson sphere or similar construct? First proposed by physicist Freeman Dyson in 1960, the concept imagines an advanced civilization harnessing the full energy of their star by building an enormous shell or swarm of solar collectors around it. If such a structure existed, it could theoretically block large portions of starlight, just like what was being seen with Tabby's star. The media and public imagination lit up. Could we be witnessing a civilization so advanced that their engineering projects could be detected across interstellar distances for the first time in years? Serious scientists dared to speak aloud the possibility of intelligent life, not on a distant planet, but through its cosmic architecture. Naturally, the scientific community responded with skepticism and caution. Extraordinary claims require extraordinary evidence. Follow-up observations were conducted with ground-based telescopes, and radio signals were sought by the SETI, Search for Extraterrestrial Intelligence Institute. Nothing conclusive emerged. No regular pulses, no structured signals, no smoking gun. Later studies suggested the dimming could be long-term and gradual, occurring over a century or more. Archival photographic plates from the early 20th century even hinted that Tabby's star might have been dimming slowly over time, a behavior almost unheard of in main sequence stars. Some researchers proposed that the star might be consuming a disrupted planet, slowly devouring the remnants of its own solar system. Others speculated about fragments of an exomoon or planetary ring system caught in unstable orbits. Still, nothing fully explains the irregularities. The dips are not periodic, and the depth varies dramatically. If it's dust, it behaves oddly. If it's debris, it's unusually persistent. And if it's artificial, well, we have no way to prove it yet. In many ways, Tabby's star embodies the heart of the scientific mystery, a cosmic puzzle piece that doesn't quite fit into the existing picture of how the universe is supposed to work. It challenges not just our astrophysical models, but also our assumptions about what we might find out there, and what kinds of questions we're even allowed to ask. And so, the star continues to flicker, watching, waiting, a silent beacon in the night sky, sending signals we don't yet know how to interpret. Whether it's a rare natural process or a cosmic signature of intelligence, Tabby's star reminds us that the universe is far stranger, and perhaps far more alive than we ever imagined. Pulsar timing. Anomalies, the broken clocks of the cosmos. In the vast darkness of space, far from the warm light of stars and the orbits of planets, spin some of the most fascinating objects in the universe. Pulsars. These are not just any stars. Pulsars are the dense collapsed remnants of massive stars that exploded in supernovae, leaving behind compact cores made almost entirely of neutrons. A neutron star is so dense that a single teaspoon of its material would weigh more than 1 billion tons. And when these neutron stars rotate and emit powerful beams of electromagnetic radiation, we see them as pulsars, the lighthouses of the cosmos. What makes pulsars so extraordinary isn't just their density or magnetic strength, it's their timing. Many pulsars rotate with incredible regularity, spinning dozens or even hundreds of times per second, emitting beams of radiation that sweep across space like a beacon. When those beams pass Earth, our telescopes pick up a pulse. These pulses are so precise that some pulsars rival atomic clocks in their consistency. In fact, astrophysicists have used pulsars to build a kind of celestial timekeeping system, mapping out not just the star's location, but also detecting subtle distortions in space-time, such as those caused by gravitational waves. But in the grand tradition of space mysteries, even these perfect clocks don't always behave perfectly. Sometimes they glitch. Without warning, a pulsar's otherwise stable spin will suddenly speed up or slow down. Its rotational frequency might jump by a tiny fraction of a percent, throwing off what was once a precise rhythm. The pulses may arrive earlier or later than expected, and the timing takes weeks or even months to stabilize again. These are known as pulsar glitches, and they continue to baffle astrophysicists to this day. So, what causes these cosmic hiccups? One leading hypothesis points to the incredibly exotic and superfluid interior of a neutron star. Beneath the crust of a pulsar lies matter so dense and strange that it doesn't behave like anything we can replicate on Earth. One idea is that the crust of the star may crack under stress, like a starquake, suddenly transferring momentum from the interior to the outer layers. This would explain the abrupt spin-up observed in some glitches. Another theory delves into even stranger territory: dark matter. Since pulsars move through the galaxy at high speeds, it's possible they interact with clumps of dark matter that distort their gravitational fields or trigger reactions in their interior. If dark matter consists of as yet undiscovered particles, perhaps with unusual properties, it might subtly affect the pulsar's rotation or structure. Still, neither theory fully explains every detail. Some glitches are massive, others are minuscule. Some occur in young pulsars, where internal movement is still active. Others show up in older, more stable stars. And, in rare cases, pulsars experience what's called timing noise. Random fluctuations in their pulse rate that seem to come and go with no identifiable pattern. This unpredictability has profound implications. It suggests that even in one of the most stable natural systems we've discovered, there's a layer of hidden complexity we don't yet understand. Perhaps our models of neutron star physics are incomplete. Perhaps we're missing a fundamental piece of how extreme matter behaves under the most intense gravity. Or perhaps these glitches are the product of quantum effects on a cosmic scale, playing out within the deepest layers of a collapsed star. Whatever the cause, pulsar glitches are more than just anomalies in astrophysical data. They're cosmic reminders that perfection is an illusion. That even the universe's most reliable clocks have moments of disruption. And in those disruptions, there may be keys to unlocking deeper truths about gravity, matter, and time itself. Pulsars challenge us not only as scientists, but as thinkers. They force us to ask, what happens when nature's most precise mechanisms go off script? What lies inside a star that spins with the fury of collapsed suns, pulsing like a heartbeat across millions of light years? And could these strange deviations be the product of new physics, or even a sign of influences we haven't yet imagined? In a cosmos that often seems to follow elegant laws and symmetrical patterns, pulsar timing anomalies stand out as glitches in the matrix, little sparks of chaos in an otherwise orderly sky. And perhaps, just perhaps, they are inviting us to look deeper, beneath the spin, beyond the pulse, and into the heart of the unknown. The axis of evil, a cosmic alignment that shouldn't exist. In 2003, astronomers studying the early universe made a discovery that left them both fascinated and unsettled. Using data from NASA's WMAP, Wilkinson Microwave Anisotropy Probe, a satellite designed to map the oldest light in the universe, they found something they didn't expect. An eerie alignment in the fabric of the cosmos. Something that didn't fit. Something that seemed off. This unexpected pattern was found in the cosmic microwave background, CMB, the faint uniform afterglow of the Big Bang, thought to be the oldest detectable light in the universe. The CMB is like a baby photo of the cosmos, capturing what it looked like when it was only about 380,000 years old. According to the standard model of cosmology, the universe should look roughly the same in every direction, what scientists call isotropy. While small temperature variations in the CMB are expected and important, they seeded all future structure in the universe. These variations should be randomly distributed. But they weren't. Instead, scientists observed that the largest temperature fluctuations in the CMB seemed to be aligned along a specific direction in space. Not only that, they appeared to point toward our solar system's ecliptic plane, the flat plane in which most of the planets orbit the Sun. This mysterious alignment, found where no alignment should exist, was dubbed the axis of evil, a term that, while dramatic, captured the sense of scientific discomfort it triggered. Why discomfort? because this alignment violated one of the core principles of cosmology, that the universe has no preferred direction. It contradicted the cosmological principle, the very assumption upon which much of modern cosmology is built, that on large scales, the universe should look the same in all directions. If this principle is wrong, or if the data is telling us something fundamentally new, it could reshape how we understand the universe itself. Initially, many scientists were skeptical. Maybe the alignment was a statistical fluke, or the result of instrumental error. Perhaps it was contamination from local sources, like dust in the Milky Way, or imperfections in the satellite sensors. But then came the launch of ESA's Planck satellite in 2009, equipped with even better resolution and sensitivity. And Planck saw the same alignment. This confirmed that the axis of evil wasn't a quirk of WMAP's instrumentation. It was real. Something somehow was causing a massive-scale directional bias in the oldest light we can observe. Something still unexplained 2 decades later. So, what could it be? Some theories propose that we're misinterpreting the data, that we're seeing an illusion caused by our perspective, or by lingering foreground interference. Others suggest more exotic possibilities, that the alignment could be a hint of new physics, perhaps a sign of non-standard inflation in the early universe. Some physicists have even speculated that the axis of evil might point toward a multiverse scenario, in which our universe collided or interacted with another in its infancy, leaving behind a directional scar in the CMB. There's even a philosophical angle. Could this mysterious alignment suggest a kind of cosmic anisotropy? That is, the universe might not be the same in all directions? If so, then everything from how galaxies form to the distribution of dark energy might vary, depending on where and how we look. The implications are profound. And then there's the most haunting aspect of all. Why does the alignment seem to correlate with our solar system? That shouldn't happen. The CMB is supposed to be completely independent of our local neighborhood. Is it just coincidence? Or does this suggest that something we still don't understand is influencing our observations? Despite the theories, no definitive answer has emerged. The axis of evil persists in CMB maps, quietly challenging the scientific consensus and resisting easy explanation. It's not as attention-grabbing as alien signals or flickering stars, but its implications are arguably even deeper. It speaks to the structure of the entire universe, and to the possible cracks in the foundations of physics as we know it. If confirmed to be cosmological in origin, this alignment may indicate that our universe has a built-in directionality, an arrow through space imprinted from a time before the first atoms formed. If not, and it turns out to be a local artifact or observational illusion, then it's a cautionary tale about the limitations of our cosmic vision. But until we know more, the axis of evil remains just that, a cosmic riddle etched in the earliest light, whispering that the universe may not be as uniform or as simple as we once believed. Galaxy Rotation Problem: The Hidden Mass of the Universe. It began, as so many great discoveries do, with a scientist asking a simple question and getting a profoundly unsettling answer. In the 1970s, astronomer Vera Rubin, working alongside Kent Ford, was measuring how fast stars moved within spiral galaxies. What they found would shake the foundations of astrophysics. Rubin was studying the rotational curves of galaxies, the way the speed of stars varies with distance from the galactic center. According to Newtonian physics, The stars at the edges of a galaxy should orbit more slowly than those closer to the center, just as planets in the solar system move faster when they're closer to the sun. In other words, the curve should decline with distance. But it didn't. Instead, Rubin discovered something entirely unexpected. The stars in the outer regions of galaxies were moving just as fast, and sometimes even faster, than the stars near the center. The rotation curves were flat. This wasn't a small deviation, it was an enormous discrepancy. The outer stars were moving so fast that, based on the amount of visible matter, stars, gas, and dust, the galaxies should have been tearing themselves apart. There simply wasn't enough mass to keep them gravitationally bound, and yet they held together. Rubin's data didn't just hint at something strange, it screamed it. The only explanation that fit the evidence was that galaxies must be embedded in vast halos of invisible matter, exerting gravitational influence without emitting light. Matter that neither emitted nor absorbed radiation. Matter that we couldn't see, but whose presence we could infer through its gravitational fingerprints. This was the first compelling, large-scale observational evidence for what we now call dark matter, a mysterious, non-luminous substance that is thought to make up about 85% of all matter in the universe. It was a revolution in how we understand the cosmos. The universe, it turned out, was not made mostly of stars or planets or gas, but of something completely unknown. But here's the thing. We still don't know what dark matter is. Decades later, we've mapped its influence on galaxy clusters, on gravitational lensing, on the cosmic microwave background. It explains the large-scale structure of the universe. And yet, no one has ever directly detected a single particle of it. We've built underground detectors to catch it. We've sifted through data from space telescopes and particle colliders. We've proposed dozens of hypothetical particles, WIMPs, axions, sterile neutrinos, and more. But the signals are always just out of reach. And that's what makes the galaxy rotation problem one of the most profound cosmic mysteries. Because this isn't a small glitch in our equations, it's a hole in our understanding of gravity itself. Some physicists have even proposed modifying the laws of gravity, creating theories like MOND, modified Newtonian dynamics, to explain the galactic motion without invoking unseen mass. These ideas remain controversial, but they underscore just how far-reaching the implications of Rubin's discovery have become. Dark matter, or something like it, is the scaffolding of the universe. Without it, galaxies wouldn't form the way they do. Stars wouldn't cluster. The universe wouldn't look like it does. Yet, we still don't know whether we're looking at an undiscovered form of matter, or whether we've misunderstood something fundamental about how gravity works on cosmic scales. Rubin's rotation curves weren't just an observational triumph. They were a philosophical shockwave. They remind us that what we see is only a tiny fraction of what exists. That reality may be deeper, stranger, and darker than we can yet imagine. In the face of this mystery, we're left with questions that shake the very framework of cosmology. What is the universe made of? Why can't we find most of it? And if we're wrong about gravity, what else might we be wrong about? The galaxy rotation problem remains one of the most enduring puzzles in astronomy, a quiet yet powerful contradiction hidden in the spin of distant stars, beckoning us toward a universe we do not yet fully understand. The universe, for all its brilliance and grandeur, is a quiet place. It doesn't speak in words or stories. It speaks in light, motion, radiation, gravity, and silence. And sometimes, in that silence, we catch fleeting echoes of truths far bigger than ourselves, whispers in the noise, patterns in the chaos, messages we don't yet know how to read. Tabby's star flickers irregularly, as if sending out pulses of a cosmic code we haven't cracked. Pulsars, the most dependable timekeepers in the sky, suddenly stutter, like instruments straining under forces we don't yet understand. The wow signal, brief, bright, and never repeated, arrived like a lone voice in the dark, a question hurled across the galaxy with no promise of reply. The axis of evil twists the fabric of our oldest light, challenging our most cherished assumptions about symmetry and order. And the galaxy rotation problem reminds us that what we can see is only a tiny fraction of what actually exists, that most of the universe is missing, not in space, but from our comprehension. Together, these 5 mysteries form a kind of cosmic poetry. They are more than puzzles for scientists to solve. They are riddles etched into the structure of reality, teasing us with a deeper truth. A truth that we, tiny beings on a pale blue dot, are only just beginning to sense. They force us to ask questions that cut to the heart of existence. Are we alone? Is the universe truly knowable? Are we seeing the full picture, or just shadows on the wall of a much greater reality? And perhaps most importantly, what don't we know we don't know? That is the nature of great mystery. It doesn't just leave you searching for answers. It expands your sense of what's possible. It humbles, even as it uplifts. It reminds us that science isn't just about solving equations or collecting data. It's about curiosity, awe, wonder, imagination. The cosmos has been around for over 13 billion years. We've been observing it with telescopes for just a few hundred. There is no shame in not having all the answers. In fact, that may be our most powerful tool, the ability to ask questions, to sit with uncertainty, and to dream bigger than our current knowledge allows. Because in every flicker, every glitch, every unanswered ping or lopsided map of the sky, there is an invitation to keep looking, to keep listening, to keep reaching into the dark, knowing it might reach back. So let the mysteries remain for now. Let them hang in the stillness between stars, because in that silence lies the next great discovery, waiting patiently until we are ready to see it. Hope you like this video. Please let us know which of these mysterious things intrigued you the most. Please like and subscribe. Thanks for watching.